We're going to walk through this one because the watch it video doesn't really tell you how to solve the equation, and that seems like it's maybe kind of important. So we have a room. I'm going to call the dimensions WLH. This is kind of like the box problem we did in class. We're given that the volume is fixed, and that's 218.75, and the volume of a rectangular room, is just length times width times height. And we're also given that the cost of the paint is 0.04 per square whatever for the walls and 0.14 for the ceiling. So since we're dealing with painting the room, we want to talk about surface area. So the surface area of the room consists of, well, let's see, we have the front and the back. So that's, let me finish drawing the room. That's 2 times the width times the height for the front and the back. We've got the sides, which is 2 times the length times the height, right? Because there's two of them. And then there's only one ceiling, right? Nope, we're not painting the floor. So the ceiling is just width times length, W times L. Okay, so let's get our cost function going, because that's the thing that we want to optimize. I'm going to call it F. If it makes more sense to call it C, then go right ahead. So however much wall there is, we have to times that by 0.04. So it's 0.04 times 2WH plus 2LH. And then however much ceiling there is, we have to times that by 0.14. So I'm actually going to change it to LW just to keep everything in the kind of same order. And I guess we can clean that up a teensy bit by just distributing that 0.04. So it's 0.08 WH plus 0.08 LH plus 0.14 LW. Okay, so that's a equation in 3 variables, and we don't want it to be. We want it to be an equation in 2 variables, so we only have 2 partial derivatives to deal with. So we use, just like in the box problem, we use our restriction, solve that for really whichever variable we want. It's going to result in the same kind of problem no matter what we do. The way I did it is I solved it for H. So I said H then is 218.75 over LW. Okay, and then I have to sub that back into, so that's going to go back into here, which is going to reduce this to an equation of only 2 variables. So F becomes 0.08 times W times 218.75 over LW plus 0.08 times L times that same quantity, 218.75 over LW. We'll get some stuff to cancel there, plus 0.14 times LW. Which is, we can clean up a little bit further, so let's just multiply this stuff out. 0.08 times 218.75 is 17.5. And then our W cancels out, which is nice, so we just have 17.5 over L plus same kind of thing, 0.08 times 218.75 is 17.5. Our L cancels out in this second expression, so that's just over W plus 0.14 WL. So we're finally at the point, we haven't really done any calculus yet. We're finally at the point where we can do some calculus. Okay, so I guess I need a new whiteboard. So finally our F of L comma W, if you wanted to call them X and Y at the beginning or whatever, you probably should, is I'm just going to rewrite this using negative exponents, because I know I have to now take some partial derivatives. So it's 17.5 L to the negative 1 plus 17.5 W to the negative 1 plus 0.14 LW. Right? So when you get to this step, you should only have 2 variables. And it might have been different if you did it a little differently, if you solved V for something else, but that's about as good as we're going to get it. Okay, so that's our function of 2 variables. We have to then take both partial derivatives, kind of the easy part, but then set them equal to 0 and solve it. And that's the thing that the video just kind of skipped right over. It's like, so solve it and you get this. So let's solve it. So f, the partial derivative with respect to L is, let's see, power rule. So negative 17.5 L to the negative 2 plus this term goes to 0 plus 0.14 W, right? Because that's just a constant times L. And let's see if I can squeeze this in. FW is going to be basically exactly the same thing. The first term goes away. It's negative 17.5 W to the negative 2 plus 0.14 L. Okay, so both of those have to be equal to 0. So there's not just one way to do this. The way I'm going to do it is I'm going to solve one of the expressions for one of the variables. So I'm going to rewrite FL as, so now I'm going to write it as not a negative exponent because I think it makes it more obvious what to do next. We know that those both have to equal 0. So oftentimes the best way to solve two equations is to solve one of them for one of the variables and then substitute that into the other one. So I'm going to solve this. Well, let's think about it. If I solved it for L, I would have, whatever my answer is, it would have a square root in it, which would work, but it would be too complex. So solve it for the variable that doesn't have a power on it. So this can be pretty easily solved for L, or for W, sorry, in terms of L. So get W by itself. So we're going to have 0.14 W equals 17.5 over L squared. And let's see, that gives us 0.14 WL squared equals 17.5. Which gives us, actually, that was kind of an extraneous step, wasn't it? 17.5 divided by 0.14 is 125. So actually, I could have skipped that step and just said, just divided both sides by 0.14 here. Okay, so ignore me. Dividing both sides by 0.14, we get 125 over L squared, which is a fairly nice even number. Well, odd number. All right, so that's gonna go back into FW. So let me again, let me just quickly write FW equals 0. So this is negative 17.5. So just some algebra tips coming at you. Plus 0.14 L equals 0. Before I don't want to stick in W as it is because it would be a compound fraction. I have to square the denominator. It'd be fine, but I'm going to multiply this entire equation by W squared to clear the denominator. One of the nice things about 0 on one side of the equation is you can really multiply the left side by whatever you want because the right side is still just going to be 0. So that's where I'm at. That's my nicest way to say that FW equals 0. I have negative 17.5 plus 0.14 LW squared equals 0. Yes. And now I stick my expression for W into this. So I have negative 17.5 plus 0.14 L times that thing squared. So 125 over L squared equals 0. And now I've turned my equation in 3 variables into an equation in 2 variables into an equation in 1 variable, which we can finally solve. So we have negative 17.5 plus, let's square that out, 0.14 L times 125 squared is 15625. That's calculator stuff. Over L to the 4th, right? We have to square the numerator and the denominator. That equals 0. Clean that up. That's negative 17.5 plus 0.14. Let's see, we get rid of one of the L's. So let's do that all at once. Sorry. 0.14 times 0.14 times 15625. It's 8 in the morning, okay, is 2187.5. over, we can cancel one of the factors of L, so we have an L cubed in the denominator. Okay, and we can solve that bad boy for L fairly easily. So let me get one more whiteboard going. I would probably just move the 17.5 over. So we have 2187.5 over L cubed equals 17.5. You can rearrange that equation. If 2187.5 over L cubed is 17.5, that means that L cubed is 2187.5 over 17.5. That's just a little kind of cross multiplication trickery that comes in handy when you have a relationship between three quantities. So that's 125, which means that L is 5. Yay! All right, hard part's over. So let's see. We had an expression already for W in terms of L. So work smart, not hard. Use that. We already figured out that W had to be 125 over L squared. And L squared is 25. 125 over 25 is 5. So look at that. The room as a square, at least it has a square floor and ceiling, right? Because L and W are the same thing. And then to get, let's see, what else do we need? We need H. So to get H, let's just use let's use our original volume thingy. Although actually we already had H in terms of W and L as well. So let's just use that. It's really doing the same thing, just two different ways. We know that H has to be the total volume divided by L times W. So that's 218.75 over 5 times 5, which is 8.75 feet or whatever it was. Okay, so the height is different. All right, and then it probably asks you for the actual total cost of the paint. So go all the way back to our F that had the 0.08 times blah blah blah, and just stick in that L is 5, W is 5, and H is 8.75. So that's just going to be like just a bunch of calculator math. So the actual total cost is something we usually want to know when we optimize stuff. We already optimized the room, but we want to know what it's going to cost to just stick 5, 5, and 8.75 back into our original expression for the total cost. Okay, what fun. Thank you.